All right, hello everyone again. You got your quiz Tuesday, unless they decide to cancel school, which I doubt they will. Didn't get much snow around me, and it's only Sunday. So I feel like we'll be in school Tuesday. You're going to take this quiz, and you're going to do fine because you're going to pay attention. All right, so let's go. We're going to go through the whole thing. I won't do every problem, I don't think, because like it says, we're only doing the odds as the homework, so I'll do some. I'm not going to do them all. Hopefully I'll do the ones you need. All right, so I will do some of these, I guess, just, for completion's sake, but, the first thing you have to do is just understand how to convert from radians to degrees. So to convert from degrees to radians, you multiply by pi over 180. So if we go 60 times pi over 180, then that just becomes 60 pi over 180. And then you have to reduce. When both numbers end in 0, then of course you can divide by 10. And dividing by 10 would give 6 over 18. So essentially it's like the zeros cancel out. Then with the smaller numbers, it's pretty clear to see. You can divide by 6, and you get 1/3. So it'll just be 1 pi over 3. I'm just not going to do another one because I think this is easy and you guys don't need it. Looking at this, for pi over 6, you can multiply by 180 over pi. That gets the pi's to cancel, but what you might notice is it also brings us to basically just 180 over 6, which is kind of what you would have expected if you just remember that pi is 180. It's almost like you're just substituting in 180 where the pi used to be to get back to degrees, and that's true. Like that works. So just think of it like that. So rather than thinking of multiplying by 180 over pi, you can think of just replacing pi with 180. The only time that doesn't work is for a radian measure that doesn't have pi in it. It's certainly possible to just have a measure of like 2 radians. And at that point, of course, there's no pi to sort of replace with a 180 so that you can convert. So for something like this, you'd have to multiply by pi over 180, and you'd end up with what? Pi over 90. I did that wrong. It'd be 180 over pi that you're multiplying by to convert. So you'd get 360 over pi degrees. And if pi is like 3-ish, then 360 over pi would be like 120-ish. And that's right. 2 radians is about 120 degrees. So there's no reason we can't have, degrees that involve pi and radians that don't. That's possible. But 99% of the time, if you're a radian angle measure, you've got a pi. So you could just imagine replacing the pi with 180 and then just doing the math from there. So we can see this gives us 30. And we could do the next one too the same way. If it's 3 pi over 5, then that's essentially just 3 180s over 5. And 180 over 5 is 36. So 3 times 36 is 108. And again, you guys will have 4-function calculators, but again, for the love of God, bring your own, all right? Because again, I've got like 10 or 12 on a good day, and when 30 of you guys show up and only 2 of you actually have calculators of your own, I'm not going to have enough. So please, can you bring your own calculator? You guys have been doing an okay job of it, but ideally I should have calculators that just sit and gather dust because you all have one. It should be all of you. Thank you. All right, so we can convert. The next thing we talked about for a little bit was arc length. And this was just sort of an application of radian measure. It's easier to find arc length when you're in radian mode. Because looking up here, here's your formula for calculating arc length when your central angle is measured in degrees. It has more components, it's more complicated. So radian measure often can simplify calculations, and I think that's the main goal of our talking about this, is just to let you know that radian measure, it's not just something that's useless. It has a use. It does simplify some calculations and make some applications easier. So in this problem, it said find the perimeter of a 60-degree slice of a large pizza that has a 7-inch radius. You could draw yourself a pizza. You could label a 60-degree central angle. That would be about this. This is 60 degrees. And the 7-inch radius would, of course, be the distance from center to the edge. Now, when they say find the perimeter, perimeter always just means the distance around the outside. So we can see for this pizza slice, our perimeter would be one radius, then a second radius, and then it would be the length of this arc. So the two radii are easy. That's obviously going to be 14 inches. But the arc is curved, so how do you find the length of that curved arc? Well, that's what this formula is for, s equals theta times r. The only problem with this formula is this formula literally only works when you're in radian mode. Luckily, 60 degrees converts pretty easily to radians. In fact, we just did it on the last slide. It was pi over 3. And again, just to work it, it was pi over 3 because we're multiplying by pi over 180. And we were able to reduce. Those both divide by 60. There's your 1 pi over 3. So if the central angle here is pi over 3, that's theta. When you see theta, it's talking about that central angle, because the measure of the central angle equals the measure of the arc. But what we want is the length of the arc. So s is going to be our 7-inch radius times our pi over 3 radians. And there's not much to do here. It's literally going to be 7 pi over 3 inches. So if that's the length of our arc, then our total perimeter would be the length of the arc, 7 pi over 3, plus the radius, plus the other radius, which doesn't really get much cleaner. We can't simplify it too much. I would just give the answer as 7 pi over 3 plus 14 inches. And that's it for that. Then we had just a bunch of these questions about calculating arc length. So these first two questions for s equals r times theta, you've got the radius and you've got the central angle. The only thing you don't have is the arc length. And both of these values are conveniently in radians. It's a little weird. I mean, 25 radians, you should know by now that a full circle is 2 pi. Well, 2 pi is only what? 3.14 times 2, so 6.28. So 25, that's like 4 complete revolutions. So when we talk about an arc, does that even make sense to have an arc that's greater than a whole circle? And of course the answer is yes. I mean, back in geometry when you defined arc, I'm sure you called it just a piece of a circle, just a part that is smaller than a whole circle. But of course, you know, there's nothing stopping us from having an arc whose measurement is a full circle plus more. So 25 radians is more than a full revolution. That's fine. You can still call it an arc. Let's do the math. Our arc length is going to be our radius, which is 2, times our central angle, which is 25 radians. There's nothing fancy here. You literally just get 50. The radians are kind of a unitless unit. I sort of tried to explain that before. It's a unit, I guess, but it doesn't really play a role. It essentially cancels out of any calculation that you're actually doing. So when we've got inches here, these are just inches. The radians, don't worry about it. When we calculate arc length, it's going to be in whatever units the radius was in. So this one's inches. Obviously 26 would be 70 centimeters. It's just going to be the radius times the theta. And I don't think these get confusing. When you get to the next one, suddenly r is my variable, but so what? For 27, if s equals r times theta, then you plug in the two values that you do know. If s is 1.5, then you plug that in. If r is your variable, then leave r alone and plug in theta. It's pi over 4, sorry. But you're going to solve the same way you'd solve any other equation. To get r alone, you're going to divide by pi over 4. Although my preference, of course, with fractions is don't divide by them, just multiply by their reciprocal, because that'll get this to cancel. That'll give me r, and then I can throw this over 1. Now I can throw this over 1, and this works out cleanly. 4 times 1.5 is going to be 6, so 6 over pi is the answer. But often if you're given a decimal, especially one like this that's easily converted, 1.5 is 3 over 2. So it might be better just to have converted that, and then maybe we would be able to multiply easier and get a better answer. If when we multiplied we hadn't gotten a nice clean integer, then we would have had integers once we were in fractional form, because the 3 times 4 is going to give an integer in the numerator. 2 times pi is going to give an integer in the denominator, well, the 2 at least. And then if the thing doesn't reduce, so what? You've got it still as a nice cleanly expressed fraction in simplest terms. But again, if we're getting 12 over 2 pi, then converting the fraction or the decimal to a fraction is kind of a moot point, because we get a nice clean answer anyway. Now, what are the units here? Well, if the arc length was in feet, then this radius must be in feet as well. I don't think I'm doing any more of these. I guess I will. I mean, 31 and 32 are a little trickier because the central angles are in degrees. So for something like 31, you'd go s equals, I really learned the rule as theta times r, so doing it as r theta has been bothering me. I'm going to do it the other way because who cares? But s is going to be 40. Plug that in. Theta is our central angle, which really cannot be 20. We're going to have to convert. So 20 times pi over 180. What's that going to be? 2 pi over 18, which is what? Pi over 9. Easy peasy, hopefully. So you go pi over 9. That's times the radius. Well, yeah. Yeah. So whatever. What we did over here was we divided or multiplied by the reciprocal. This will be the same thing. So I'm going to take my own advice, multiply by the reciprocal rather than imagining it as division. So 9 over pi gets multiplied. That'll cancel, give me r, and then I guess I'm looking at 360 over pi. And we're solving for a radius in a problem where the arc length was in centimeters. So that radius is in centimeters too. That's it. Those are kind of easy. Then for this batch of problems, it got a little bit trickier because they were talking about concentric circles, but I explained to y'all that concentric circles were just circles that shared a center. So if I center a circle at that point, we'll let it be blue. I think it's going to be blue anyway. Yeah, blue. Then we can widen this and have a different circle. Well, these circles are concentric circles because they share the same center. And so the takeaway from these couple of problems was supposed to be that if I don't know theta, if I don't know my central angle, that's okay, I can figure it out because I can just imagine some angle. And my drawing might be way off. I'm drawing an acute angle and maybe this angle is going to work out to have to be totally obtuse. Maybe it's going to work out that it's more than a full rotation even, but it doesn't matter. I just need to be able to understand what's happening here. And so hopefully what you can see is, of course, the blue circle is giving us a smaller sort of inner radius, and it's of course cutting this arc here. So that'll be S1. And when you go to the red, you've got this longer radius. And so that would necessarily be cutting a longer arc. If you compare this dark red arc to this, dark blue arc, then if you were to straighten these out, obviously the red one's going to be longer than the blue one. And the interesting thing is supposed to be that they're both cut by the same central angle. So I'm drawing this to be about 60 degrees. Well, of course 60 degrees would cut a smaller arc from a smaller circle. So we can take that the central angles are the same. It's only the radii and the arc length that are different. That's kind of the trick here. So once you get that, you look at this and you see that you've got R1 and S1. So you've got the radius of the blue, it's 11. You've got the arc length of the blue, it's 9. So using that information, you can figure out theta. And then once you know theta, you can find the other arc length because you know that guy's radius is 44. Now, I don't know, better question is are these things just proportional? if this radius is 4 times greater than this radius, does that mean the arc length is going to be 4 times greater, or is there something deeper going on here? Your intuition might be telling you that it is just going to be 4 times longer, and it is just going to be 36. But our intuition can fail us sometimes in math, so I'm gonna jump through the hoops and do it all, and then we can talk about what we discover. But let's go ahead and just say that S1 has to equal theta 1 times R1. Let's remind ourselves that really there is no theta 1. There's just theta. The two angles, or the two arcs, share the same theta. So substituting in S1 was 9. Theta is what I'm solving for. The radius was 11. So in radians, my central angle is 9 divided by 11. Which means my drawing is pretty good, because 9/11 is pretty close to 11 over 11, which is 1. And we know that 1 radian is about 57 degrees. So this should be, a little less than 57 degrees. 50-degree angle is about right. Anyway, we can now find the second arc by taking our theta, multiplying it by our second radius. So we're solving for S2, so that's our variable. Theta is going to be the same theta because it's the same central angle. So 9 over 11 multiplied by the new radius, which is 44. And lo and behold, if you cross reduce, you get 4. 4 times 9 is in fact 36. So your intuition was right here. That's centimeters. Yeah. So if you had that intuition that, quadrupling the radius would quadruple the arc length, then you're right. If you're remembering a time when that wasn't true, that wouldn't have been true if we were talking about the area. If we were talking about the area of these sectors, then this blue pizza slice versus this overlapping red pizza slice, this whole thing, well, quadrupling the radius does more than just quadruple the area. It multiplies the area by a factor of 4 squared. So when you multiply a linear dimension by 4, your area, your two-dimensional dimension, gets increased by a factor of 4 squared. So there's 16 times as much red area here as there is blue. Picture not drawn to scale. This red has a radius that's less than double the other one. It's supposed to have been increased by a factor of 4. If I drew that more accurately, you could tell that the red is way, way, way bigger than the blue. Anyway, I think I'm probably getting confusing here, but when it comes to just length, if you double a length, then any corresponding lengths also double. If you quadruple a length, then any other pairs of corresponding lengths will also quadruple. Area, though, gets increased by a greater factor. You might remember that from geometry. Moving on. So this is all the same. I'll just run through it because I can run through it quickly. But it says if you had a 10-degree sector cut from a circular disk, 10 degrees means central angle 10 degrees. So we're talking about a small slice, 1/36th of the whole circle. So the radius is 11. They're saying find the perimeter. So perimeter again will be radius plus this little sliver of an arc. So our perimeter is going to be just 11 plus 11 plus whatever our arc is. So let's figure out what our arc is using our formula. Theta times r. S equals, now theta, again, at 10, you can't plug in 10. You have to be in radians. But 10 is going to be, you multiply by pi over 180, so that'll be 10 pi over 180, which reduces down to 1 pi over 18. Then you multiply that by the radius, which is 11. And you get 11 pi over 18. That's it. So we know that our perimeter is going to be 22 plus 11 pi over 18. And I don't see any great way to simplify it, so I'll leave it alone, and I'll call it inches. That's it. 36 is 100 degree within it to the nearest centimeter with the radius of the circle. This seems straightforward to me. So when they say 100-degree arc, they're giving you theta. But they're giving it to you as 100 degrees, so you know you'll have to convert that to some number of radians. The arc length has a length of 7, so they're giving you S. and they're asking you to find the radius. So this is no different from the problems before, where you knew two things and had to find the third thing. You just plug into the formula and see what you get. So there's nothing special here. 100 degrees would be 100 pi over 180, which would be 10 pi over 18, which would be 5 pi over 9. And if s is equal to theta times r, then 7 is equal to 5 pi over 9 times r. And again, my preference for clearing this fraction is just to multiply it by its reciprocal. That goes over 1. These cancel out. You get a radius of 63 over 5 pi. And that's going to be centimeters. So that's that. You would leave your answer like this. The one thing that's slightly worth saying is if you were going to type this into your calculator, if you wanted to figure out what 63 divided by 5 pi was, well, on a TI calculator, if you type in 63 divided by 5 pi, then your calculator does work as it comes to it. So it's going to do 63 divided by 5 first, and then multiply by pi. So that actually ends up giving you the answer to 63 pi over 5, which is not really what you want. So you have to be really careful when you type something like this in, is you have to actually say, all right, I want 63 divided by, and then put parentheses around the 5 pi. The parentheses mean your calculator will now do that calculation first, then divide, and that'll give you the right value. Again, you don't have calculators, you won't be using them anyway, so just do it by hand, just for future reference. Reminding you to be really careful with calculators and use parentheses when you need to. Okay. So we did this one in class for both classes, so I don't think I'm going to do it again. If you didn't pay attention, call a friend who does pay attention, and they should have the notes to share with you. I'll try to explain it at least a little bit for someone who wants to do it, but the question talks about there's 10 identical pieces to form a circular track. I don't know, think about those train sets from IKEA. I don't know why I said IKEA, they can come from anywhere. Mine's from IKEA. But they've got these little puzzle piece ends so they fit together. And so you got the straight piece, and you can attach your little curvy piece that starts to go around, and you can make a circle. I think, if I'm thinking about my son's set, I think it takes 6 pieces to make a full circle. So for him, if we had this, it would be like that. There'd be 1, 2, 3, 4, 5, 6. This particular one says it takes 10 identical pieces. Who cares? I'm not even going to try to draw it. Well, sure. I'll try to draw it to scale, kind of. It's going to be, I'm going to need 5 on one side. 5 to the left, 5 to the right. Oh God, what have I done? So sure, imagine just cutting this whole thing in half and then cutting the other side into 5 equal bits to the best you can. I could put a line here, here, here. So there's 1, 2, 3, 4, 5. The other side, if I did it cleanly, I've seen better, I've seen worse. Anyway, this is what they mean. Here's one piece of track. So just to define variables, you've got an inner radius, R1. You've got an outer radius, R2. And when you see this 3.4 inches shorter, that's basically telling you that R2 minus R1 is 3.4. So they're not giving you R1. They're not giving you R2 either. They're just telling you that R2 is 3.4 inches longer than R1 is. That's all you get. The other thing you know, though, is you do know your central angle theta. And you know that because you know that these arcs are 1/10 of a full circle. So 360 divided by 10 tells you that we're dealing with 36-degree central angles, which is the same as pi over 5. The answer to the question, where it says, what's the width of the track? Well, the width of the track would be the distance along this edge. Which I'm realizing now I screwed up. So here where I said R1, I was pretty clearly talking about S1. Hopefully you forgive me. We're talking about the shorter arc length. Arc length was S. And here where I said R2, I of course meant S2, arc length 2. And so of course it's S2 minus S1. That actually equals 3.4. The width, the thing we're actually trying to solve for, is the difference between the radii, R2 minus R1. Because if I could find the radius out to the outer circle, if I could find the radius out to the inner circle, then the width of the track is the difference between those two measurements. Again, pretending that one radius was 12 inches and the other radius was 8 inches. Then obviously the width of the track is 4 inches. It's the difference between the two. So the other thing to remember here is that, of course, theta 1 and theta 2 are the same angle. They're both pi over 5. So the trick to solving this problem, we said, was you actually have to write a system of equations where S1 would be equal to theta times R1, S2 would be equal to theta times R2. And since both of our, variables here seem to be involving differences where we've subtracted, that's exactly what we'll do. We'll subtract the two equations from our system to generate one new equation. Now I want to be subtracting so that I get S2 minus S1. I want the bigger one to be the one I'm subtracting, so go S2 minus S1 in that order. I guess I'm doing the whole problem at this point, by the way. Then you'll go theta R2 minus theta R1. And because theta is the same, we can factor it out. So S2 minus S1, we've already said, is the 3.4. So we can just substitute that in for this entire expression. I still don't know S1 or S2 individually, but I know that when I'm doing subtraction, it's going to be 3.4. If I factor out theta, then I get theta times R2 minus R1. And then the magic here is I know theta. We said it's pi over 5. And I actually also know R2 minus R1. That is the thing called the width. So I can substitute in for this expression too, just call it W. And finally, I'm at a simple place now where all I have to do to solve is multiply by the reciprocal of pi over 5, which is 5 over pi. So I can get these to cancel, and I can see that my width is going to be whatever 5 times 3.4 is. And I've got a calculator, so I should be able to do it. What is it, 17? I think it's exactly 17. So you get exactly 17 over pi. And our units are in inches, so this must be inches. That's our width. So there's your thought process for 37, which, yes, you do have to have done, because it's odd. I see I snuck off the bottom of my little window here. So there you go. Scroll down. There's the answer. Yeah, you got to know that. Moving on. 38, I don't think I care. It's basically the same as 37. It's also even, so you don't have to do it, so I assume none of you will. And cat out of the bag, I don't think there's going to be a question about concentric circles on the quiz anyway. There'll be an arc length question, but it won't involve concentric circles, I don't think. So we can move on. And then we get to, I don't know, phase 2 of the unit. So in phase 2 of the unit, we're going to finally start talking about some vocabulary. Standard position we defined, coterminal we defined, initial axis or initial ray, terminal ray we talked about. Reference angle was another big one. And we do define it later in the packet, but I like to just put it here. While we're doing vocabulary, let's cover all the bases. So remember, a reference angle is the acute angle formed by the terminal ray and the x-axis. So for an angle like this that they're calling alpha, that looks like it might easily be 140 degrees. Well, if I've rotated 140, then it shouldn't be too tough to see that it would take an extra rotation of 40 degrees to get back down to the x-axis. So the acute angle formed by the terminal ray and the x-axis would be that angle right there. It would be 40 degrees because essentially you're just doing 180 minus the 140. And we can see that for a 140 degree angle, the reference angle would be 40 degrees. We'll do more with that as they come up. We redefined all of our trig functions. You know, SOHCAHTOA, sine, cosine, tangent. It's been treating us great. It was wonderful when we first learned it in geometry. Maybe we revisited it in Algebra 2 and everything, but its days are numbered. It's not what we really want to be doing in calculus. So it's actually going to be more convenient to think of sine not as opposite over hypotenuse, but as y value divided by radius. Now why? Where's that coming from? Well, because if you imagine an angle in standard position, meaning with its initial ray on the x-axis, with its terminal ray rotating through some angle measure, call this theta, then we see that we could always draw a circle. Our terminal ray will always intersect that circle somewhere, and that point of intersection with this circle has to have some coordinates. And if you think about the way the Cartesian coordinate system works, right, the regular xy plane, okay, what else is it called? Cartesian coordinate plane? Does it have a rectangular? It's also just called the rectangular coordinate system. But those coordinates, x and y, they are literally defined as the horizontal distance from the origin over, then the vertical distance from the origin or the x-axis up. But that x and that y will always be the horizontal leg and the vertical leg of some right triangle. And that right triangle will always have a hypotenuse that is the radius of the circle that you've drawn. So there's just a clear analogy here between the opposite side of the angle in a right triangle and the y coordinate of some ordered pair, right? The opposite is this vertical guy, it's the y value. The adjacent side is x. And the hypotenuse is r. So in quadrant 1, it might not feel terribly important to make this distinction, because if my angle is, I don't know, 82 degrees, then all of this math lines up nicely. But all you have to do is let the angle grow to be more than 90. Suddenly, if you have a rotation angle that kicks you over to there, then it gets a little bit harder to picture a right triangle that has a 100-degree angle in it. That's not really possible from geometry's standpoint. And hopefully some of you are thinking, yeah, Mr. F, you just draw the triangle on the other side. And you're true. You're right is what I should have said. That's true. You're right. When you do that, you've got this angle. Let me call it alpha, I guess. Why not? But alpha has some corresponding reference angle that we could call beta. And beta defines a triangle for us, doesn't it? Beta defines a right triangle like usual. We've got opposite, adjacent, hypotenuse. So it's all true. I admit it. You got me. You backed me into a corner. I have to admit that it doesn't matter. Whether you're doing opposite over hypotenuse or whether you're doing y over r, it doesn't really matter. But embrace these new definitions regardless, because it's the one we're going to use. We talked about how there's a function that's the reciprocal of sine. It's called cosecant. There's a function that's the reciprocal of cosine. It's called secant. And there's a function that's the reciprocal of tangent called cotangent. Study this. There's nothing I can say that explains why things are what they are. Things are just what they are. So memorize this page. I'm not gonna pretend that's easy to do necessarily, but you guys know how to study. You can make flashcards if you want to. Do what you got to do. Repetition. Write it. Take a piece of paper and just write it 20 times each. That's what I used to do, literally. Anyway, moving on. Bonk. So going back to this idea of coterminal, the easiest way to think of coterminal, in my humble opinion, is if I had an angle, how about 100 degrees? Well, that is a counterclockwise rotation. Maybe the simplest coterminal angle would be the clockwise rotation that lands me in the exact same spot. And hopefully it's clear to you that these two angles together would have to make a total of 360 degrees. So if I said this initial angle was 100, then it would be related to a 260 degree angle. 360 minus 100 is 260. If I'm going the other way around, then I call that a negative angle. but negative 260 and positive 100 are going to have terminal rays that stop in the exact same spot in quadrant 2. But that's not all. Another way to think about this is I could have an angle that's 100 degrees, and then it just continues to whip around another entire rotation. So adding 360 to 100 would give me 460 degrees, and that would be coterminal with the 100. And then I could just do that again. I could rotate 100 and then go 360, 360 twice instead of only once. Or I could do it 5 times instead of only once. But to me, the angles that are coterminal with 100 are going to be the angles that are 100 plus multiples of 360, right? If I add on 360 times 1, times 2, times 3, times 4, 5, 6, 7, 8, then that's going to generate a bunch of coterminal angles. So for a problem like this, I just want you to recognize who's not coterminal. You just have to spot the one that's not a 360 degree difference between the 150 and everybody else. So I don't know. Let's just do 150 plus 360. That makes 510, which is literally the next guy on the list. So you know that they are coterminal with each other. The next one is negative, so you could go 150. There's nothing sacred about adding 360. I guess I should have made that point down here. But if I rotate 100, I could then sort of rewind by 360, landing in the same spot. So you could subtract. So maybe you could think of this as plus or minus. You know, it's 100 plus or minus 360k. And I guess just to explain this as a foreshadowing thing, rather than saying plus or minus, maybe I could just stipulate what kind of number k has to be. If we wanted k to be a negative, that would cover the subtraction. So we could let k be an integer. Then I have positive whole numbers that push me forward onto the larger angle measures. And if I'm an integer, then I can also have negative whole numbers that, you know, subtract 360 and give me all the smaller coterminal angles and the negative coterminal angles. But sure, there's an expression for all the angles coterminal with 100. Speaking of, let's subtract 360. We get negative 210, which is not surprisingly the very next number on our list. Then we get 450, which hopefully sticks out like a sore thumb. When we added 360, that hopped us all the way to 410. So clearly, to 510. So clearly we hopped right over 450. 450 is not coterminal with us. Scratch that guy out. Now the 870, what's that? Must be 150 plus 2 360s. 2 360s being 720, being 870. So there's your 870. There's your verifiable proof that these 4 angles are all coterminal, but 450 is different. Alright, so I know 2 is even and you technically don't have to do it, but because it's in radians, we should do it. Because you got to make sure you can handle radians. Now your thought process should be the same. Dang it. Dang it again? I guess that's fine. So for radians, well, in radians, a full rotation, instead of being 360, is just 2 pi. So I guess one way to do this problem is take the 5 pi over 3 and add 2 pi. Or take away 2 pi and just see how many of these other angles are 2 pi radians away. Because if they're exactly 2 pi radians away, then they're sitting in the same position in the coordinate plane and they're coterminal. So adding 2 pi, well, 2 pi over 1, if you multiply by 3 over 3 to get a common denominator, is 6 pi over 3. So adding gives 11 pi over 3, which I think is on our list. 11 pi over 3 is just 1 rotation more than this, so those guys match up. Then you've got negative, so I guess we're subtracting. So 5 pi over 3 minus 6 pi over 3 gives negative 1 pi over 3. Which isn't even on our list, and that's fine. But then I could take that and subtract again. That gives me negative 7 pi over 3, which is this guy, so those guys are coterminal. But you may notice we hopped right over this guy. So this guy is not a full multiple of 360 or 2 pi away. which means the 365 pi over 3 must work. So why? How could I prove to myself that that works? Well, you could take the 365 pi over 3, and you could subtract from it the 5 pi over 3. That leaves me with a difference of 360 pi over 3, aka 120 pi. I'm probably off screen right now, aren't I? Yep, I went too low, but I can extend. So I'm talking about 120 pi. This is the difference between those two angles. And that difference, of course, is 60 2 pi's. It's exactly 60. So it's exactly 60 full rotations. So that is telling me that if I'm sitting at 5 pi over 3, which by the way is 300 degrees. Yeah, 300 degrees, which is in this position right here. So 5 pi over 3 is this rotation angle. So 365 pi over 3 is just this rotation angle, and then someone whips you around 60 more times, but it's exactly 60. So you know that after a whole mess of spirals, you do stop again at exactly the right position. So yes, they're coterminal. You can just check that the difference between them is evenly divisible by 2 pi. There, I said that 100 ways now. We can move on. All right, so now for something kind of completely different. It says evaluate the 6 trig functions of angle theta. So angle theta is this rotation angle that has us living in quadrant 2. Now they very kindly are handing us x and y on a silver platter. Now after all that talk a second ago about coterminal angles, you'd be forgiven if you forgot that in this lesson we also redefined sine, cosine, and tangent in terms of x's and y's and r's. So it seems to me that for number 3, if I want the sine of theta, the cosine of theta, tangent theta, secant theta, cosecant theta, cotangent theta, then all I need are those x, y, and r values. In fact, I've got tangent and cotangent already, because tangent is literally y over x. And they handed me those values. They're 2 and negative 1. So the tangent is going to be 2 over negative 1, or just negative 2. There. I've done one of these 6 things already without even having to do any math. Cotangent, by the way, is just the reciprocal. It's x over y. So that's going to be negative 1/2. So there. That's 2 down out of 6. There's only 4 left. Now the problem is all the rest involve r. They only gave me x and y. I need to find r by myself. And for this, we're better off zooming super far in. That's probably way too far. Nope, it isn't. So with 8 times the magnification, then you might notice that from this point we can drop straight down. We can build ourselves a nice lovely right triangle. A right triangle where this horizontal leg has a length of 1. Technically it's negative 1 because we went to the left. And the vertical leg has a length of 2. And our radius is this hypotenuse. Because if you're imagining that circle that we pass through, that's not my best circle, but the radius of the circle that this terminal ray passes through is the hypotenuse of this right triangle. So all you need to solve for r is the Pythagorean Theorem, where a squared plus b squared equals c squared. Which actually means for us, a and b are the legs. The legs are always going to be x and y. And the hypotenuse is always going to be r. So it's like you may as well just memorize this sort of new version of the Pythagorean Theorem for trig, which is that x squared plus y squared always has to equal r squared. And then we can just do this math. We're going to go negative 1 squared. So you see that the negative doesn't matter because we're squaring it anyway, so it's going to come back positive either way. You get 2 squared. I think that's probably going to be 4. And then that equals your r squared. So I guess 5 is equal to r squared. So take the square root, and root 5 is going to be r. So easy, we found our radius. So shrinking back to our best fit. There's all that math again. I think you can still read that It's a little small, but that's okay. If you can't read it, rewind the video and it'll get bigger. So r is root 5. That means finding the rest of these should be cake because we have memorized that sine is y over r. That means it's 2 over root 5. And I know I told you guys that it's okay to leave radicals in the denominator, but it's not. For trigonometry, you really shouldn't. For trigonometry, we need to get in the habit of cleaning these up. In other settings, if you had a radical in the denominator, I wouldn't really care. But for trig, I kind of do. So to clean up your denominator, by the way, it's a process called rationalizing the denominator, because square root of 5 is irrational. Maybe you remember what that means. But I want to make it rational again. Or, more to the point, I'm just going to turn it into an integer by multiplying it by itself. Because root 5 times root 5 becomes normal 5. So then you end up with 2 times root 5 in the numerator. Now, I'm not trying to say that this is cleaner. This is definitely uglier than just having 2 over root 5. But that's the preferred answer, 2 root 5 over 5. For reasons. Somebody in period 8 asked, like, hey, why? Like, why do we even bother? And the answer is it goes back in time, like before people had calculators. Calculating the approximate value of this by hand is simpler when the denominator is an integer. You can do the division more easily when the thing that you're dividing by is an integer rather than an irrational number. And so that's why, like, you know, hundreds of years ago, it was important to have integers in your denominator. It's no longer true, but sorry, you gotta do it anyway. Hey, guess what? The reciprocal of sine is cosecant. So this answer that we already found, we can recycle it. Cosecant's going to be r over y. So if you use the answer that you had before you flipped everything, then flip this. The 2 over root 5 becomes root 5 over 2. And then you don't have to clean anything up. You've just got your answer. All right, now cosine is just x over r. That means it's going to be the negative 1 over root 5. That's going to be, when you clean that up, root 5 over 5. So that's cosine. Now secant will be the reciprocal. So that's just going to be root 5 over 1, aka root 5. Now it's still negative though. It's root 5 over negative 1, so it's negative root 5. But there you go. From just being given a point in the coordinate plane, that point defines some terminal ray, which with an initial ray creates some angle, and then from that angle we can find all 6 trig values. So there you go. That's how you do 3. 4, 5, 6 are all going to be the same basic deal. I guess since 5 is odd and it's technically assigned to you, I'll try to help you with it. When you do your math, you should find the radius to be root 2. And then you should find sine, cosine, tan. Am I too far down? Yep. Okay, so sine, cosine, tan. Reciprocal of sine is cosecant. Oops. Sometimes I forget the theta. Don't do that. It's actually super bad. If you were to just write tangent, then what you're really doing is you have tangent of, right? Tangent is a function, and if you just write tan, it's like you have tangent and then it's just empty inside, which is sort of tantamount to being like 3x plus the square root of nothing minus 7. Like, how awful does that feel to just see a radical with nothing under it? It makes no sense. Well, writing tangent where tangent's not evaluating anything, that makes no sense either. You can't just leave the theta off of it. You have to actually write it. Otherwise it looks like abject nonsense. So hear me on that. That's important. All right. All right, so blah, blah, blah. We've got all our stuff. And this should be even simpler because x and y are the same number anyway. So that's actually going to mean sine and cosine are the same. Because for sine, I do y over r. So I get negative 1 over root 2. Which, when I rationalize, is negative root 2 over 2. But the x-coordinate is the same as the y. So, of course, the cosine is going to have the exact same value. It'll be negative root 2 over 2. And then, somewhat interestingly, tangent is y over x, so it's negative 1 over negative 1, which is positive 1. Because when you divide two things that are equal, of course you get 1. So tangent actually has a nice clean value. And cotangent as the reciprocal would be negative 1 over negative 1, which is 1 again. And then the reciprocal of sine is going to be, what, negative root 2 over 1? So negative root 2. And of course secant be the same thing. So there, I did 5. You're on your own for 4 and 6. Figure them out yourself. All right, so these are more of the same. It says P is a point on the terminal side. It's literally more of the same. The only difference is here they drew the picture for you. Here you'd have to draw it yourself, which is actually somewhat good practice, because a very important thing that's coming is knowing into what quadrant you fall. So for 7, with both coordinates positive, if I'm over 3 and up 4, obviously I'm in quadrant 1. Also, I can imagine my right triangle. I've got my horizontal leg is 3, my vertical leg is 4. My hypotenuse, if you do the math, is going to turn out to be exactly 5. So given all that data, could you find all 6 trig functions? Yeah, of course you could. You just plug and chug, right? So sure, sine is what? Y over r? So 4/5. Cosine will be 3/5. Tangent will be 4/3. Then the rest are the reciprocals. So 5/4, 5/3, 3/4. Sorry if I'm going fast, but I just don't feel like doing this. Here's your sine, cosine, tangent. Cosecant. Secant, cotangent. There you go. That's 7. I'm just not going to spend a ton of time on this because I gave you guys a chance to ask questions in class and you didn't. So most of y'all should understand this. If you've tuned in because you didn't understand this, then I apologize for going so quickly. But I didn't go quickly through the previous ones. So hopefully you got the main ideas from there. And now for the next few, you really just are here for answers. So we're not doing 8. We'll do 9 because I assigned the odds. Now 9's a little weird because it has a 0 in it. So for 9, if I'm in the point 0, 5, then that means I'm straight up here at 5. Now here's where the x, y, r definitions do come in handy, because I literally can't draw a right triangle this time. It can't be drawn. It kind of dies for a moment when you're on the y-axis. Now if I was in this quadrant, I could break it down and make my right triangle. If I was in this quadrant, I could make my right triangle. But on the axis, there's literally no triangle for you to see. But even without a triangle, our definitions of x, y, and r, those still remain. Because we just have an x coordinate of 0. No big deal. We have a radius of 5. And then kind of weirdly, oh, I said it wrong. Our y value is 5. Now our radius is 5 as well. They would both be 5, right? Just that's the deal. The y value and the radius are the same at 90 degrees. Just like the x value and the radius are the same. Well, slight difference there. At 180, the x value would be negative, and the radius would still have to be positive, because the radius must always be positive. So anyway, given these values, can I still find my sine, cosine, tangent, and my blah, blah, blahs? Sure. Sine is y over r. So that means it's 5 over 5, which is 1. But cosine is x over r. Yeah, so it's 0 over 5, which is 0. And tangent is y over x. So tangent is 5 divided by 0. Well, 5 divided by 0 is undefined. So I think for the first time we're seeing a trig function that's undefined. The instructions did stipulate that you might get that, so it shouldn't be too shocking that we did get it. All right, now the rest are reciprocals. So cosecant is r over y, which is 5 over 5, which is still 1. Then for secant, it's going to be r over x, so 5 over 0. So we get another one now that's undefined. And then cotangent is x over r, that's 0 over 5, so that's just 0. So again, who are all these? Well, it's sine, cosine, tangent in that order. Then the reciprocal of sine is cosecant, and then secant, and then cotangent. So there's your 6 trig values. I'm not doing any of the evens. I'm not doing 11 either. Hopefully this is enough to get you through. Okay, so this is different. This was confusing to a lot of people because most people looked at 13 and they figured this was an ordered pair. They figured, okay, don't go left or right at all, and then go up by pi over 2. But that's not it. You got to read directions. It says, state the sign of t in the interval given. So this is interval notation. So again, 0 comma pi over 2. First of all, if you understand that these are representing angle measures, then they're talking about 0 degrees to 90 degrees. So they're saying, talk to me about sine of t for a range of t values where t falls between 0 and 90. That's what they're talking about, which really means that all they're talking about is any angle that lives in quadrant 1. Because here's 0, here's 90. So if I'm an angle that's living between 0 and 90, then I'm just an angle that lives in quadrant 1, which suddenly makes this easy because A, sine is y over r, but r is always positive. But you can see that in quadrant 1, the y values are always positive. Well, so are the x's, but it's going to be a positive number over a positive number, so of course sine is going to be positive. Now cosine is x over r is always positive, and x is always positive too if you're in quadrant 1. So it's plus over plus, so that's plus. And tangent is y over x. So if tangent is y over x, then in quadrant 1 you're still doing a positive over a positive, so you're positive. So that's that for 13. For 15, they've got you rotating into the next quadrant. So 14 has you living in quadrant 2. Because it says be greater than 90 but less than 180. So 15 just has us down in quadrant 3. I will gently remind you that of course x's are negative and y's are also negative. So it seems to me that the sine of t in quadrant 3 is going to be negative because it's based on the y coordinate. So a negative y divided by a positive radius means sine will be negative. Then cosine, well, that's based on x, which is still negative. So an x over a radius is still negative. Instead of these negative signs, which just look like I'm making a blank, why don't I write out negative? Negative. Then you come to tangent, and we kind of saw this already, somewhat interestingly. Remember, it's y over x, which in quadrant 3 is kind of special because it'll be a negative divided by a negative. And that is, of course, a positive. So although it seems like both coordinates are negative, so sine and cosine are negative, it's not like everybody's negative. Tangent would still come up positive. And don't forget cotangent would too. Because it's just the reciprocal, x over y, which would still be a negative over a negative, which is still a positive. So this bank of questions, by the way, was meant to explain the all students take calculus mnemonic that we talked about. So as your angle rotates through 360 degrees, we said in quadrant 1, all trig functions are positive. Sine, cosine, tangent, secant, cosecant, cotangent, they're all positive. But when you're in quadrant 2, the only trig functions that are positive are sine and its reciprocal, cosecant. By the time you rotate into quadrant 3, sine and cosine are negative, but tangent's positive, and its reciprocal, cotangent. So that's what these letters mean. They're telling you which trig functions are positive. In quadrant 1, all are positive. In quadrant 2, only sine is positive, and it's reciprocal too. It's reciprocal also. Over here, tangent, and that must mean that over here, cosine is positive. Again, why? Because cosine is based on x. So it doesn't matter that I'm down here. It matters that I'm to the right, because it's the x value, which is positive, so it's cosine. And secant, of course. But that's that. Moving on. Click. We are 20 minutes away from an hour-long video, so I'm going to stop soon. But I'll do these. For 17, all you got to do is figure out where 143 degree is. And 143 is certainly more than 90, but it's not as much as 180, so it must be sitting in quadrant 2. And given that it sits in quadrant 2, and given that cosine is about x values, you know that this thing is negative. Let's do 18 because these are fast. 192, it's more than 90. It's even more than 180, but it's not more than 270. So we're going to be here in quadrant 3. In quadrant 3, everybody's negative, except for tangent and cotangent, and they asked us about tangent, so we'll be positive. Then the 7 pi over 8. So this is a little trickier. Until you remember that 180 is pi, which expressed in eighths is 8 pi over 8. So as soon as you realize that 180 degrees is 8 pi over 8, 7 pi over 8, you can tell, is just going to be an angle measure that comes up a little bit short of 180. So you know you're in quadrant 2. It doesn't take any actual computation, right? You just know that 7 pi over 8 is almost 8 pi over 8. So you're in quadrant 2. It's cosine. Cosine is x's, so we're negative. Because we're in quadrant 2. And finally, 4 pi over 5. Same trick. 180 is pi, which expressed in fifths of pi would be 5 pi over 5. And 4 pi over 5 comes up a little short again, so you're in quadrant 4 again. And it's tangent. So tangent in this quadrant with a negative and a positive would be a positive divided by a negative, which is negative. But there you go. So notice you don't have to actually evaluate here. You just have to decide if the answer is positive or negative. These again. Okay, fine. For 21, it says decide which ordered pair could possibly lie on the terminal side of theta. Theta being 45 is here. This is a review after all, so I don't really need to pull my punches, I guess. You guys have already learned that for 45 degrees, you should already know that the coordinates are root 2 over 2 and root 2 over 2. You should already know that if we're talking about a unit circle, then the radius was 1. That's how we got these coordinates, and we used a 45, 90 reference right triangle. Well, normally this triangle doesn't work like this. Normally you would have said probably xx and x root 2. So the question is really just which of these points holds that ratio. It doesn't have to be root 2. If the legs were both 2, does that work? Sure. If the legs are both 2 and then they're equal, that's all that really matters. With a 45 degree angle, you needed x and y to be equal, so A is the right answer. B and C could never work because they weren't equal. The legs have to be equal for 45, 90s. The hypotenuse doesn't have to be 1 because not every circle is a unit circle. In fact, the circle where these x's and y's are 2's is a circle of radius 2 root 2. And that's fine. It can be any circle. It's all about the ratios. Now for 22, this was 21. For 22, 2 pi over 3 is 120. So the first thing you could do, since you know you're in quadrant 2, is pick the answer that's actually negative positive. I bet there's answer choices that just don't even follow the right signs. So negative positive, okay, I was wrong. All three choices are at least negative positive, but imagine for a moment if there was secret option D where they were giving you root 3 comma negative 1 as an option. I mean, you'd throw that out right away, of course, because that lives in quadrant 4, and the given angle has to live in quadrant 2. So that at least helps a little. Now, more importantly, I said 2 pi over 3 was 120 degrees. So that's a 60 degree reference angle. So we're going to use our 30, 60, 90 rule, which says the shortest leg is x, the hypotenuse is 2x, and the long leg is x times root 3. So basically we're just looking for that relationship again, where the x coordinate is whatever, and the y coordinate is the x times root 3. So it ain't this, these guys are equal, that would only be for a 45-degree reference angle like we saw in 21. Here, x is 1 and y is times root 3, so yes, that is the right ratio. X should be small and y should be big. Over here they have it backwards. They've got a big x value and a small y. That would be a 30-degree reference angle. This would be 150 degrees. This would be 5 pi over 6 is what that would be. So it's wrong is what that is. So 22 is B. I'll leave you all to the rest. Have fun with that. Okay, and now, these are very important, like super important. So important that I'm going to hide most of these. Okay, so focus on just this one. So they're telling you to find sine theta and they're telling you to find tangent theta. And they're telling you to do that given that the cosine of theta is 2/3 and cotangent is positive. So cotangent is greater than 0. That means positive. All right. So what's the point? Well, the fact that they gave us cosine is super helpful. It's really helpful if they had asked us to find secant, because you wouldn't have to do any math at all. You would instantly know that secant is 3/2, because it'll just be the reciprocal of the one they gave you. But if you want sine, then sine, remember, is y over r. They gave us cosine. Cosine is x over r. So in kind of a backhanded, sneaky way, they have told us that x is 2. And they've told us that r is 3. Colon equal sign. What we don't have is y. And we need y, because sine is defined in terms of y, and so is tangent. Tangent is y over x. So all I really have to do is figure out y. And we actually know how to do that. We said it's just Pythagorean Theorem, a squared plus b squared equals c squared, but we actually generalized it to x squared plus y squared equals r squared. And they conveniently gave us two things. So I guess I'll plug in the 2 for x. Y is the variable I'm solving for. R is 3. So I guess that's a 4, that's a 9. So y squared must equal 5. So y equals, all right, here's where we get it. It's plus or minus root 5, isn't it? Now it can't actually be both. And so this is where we have to decide whether we're positive or negative, and good news is it just all depends what quadrant theta is in. Are we in quadrant 1, quadrant 2, quadrant 3, or quadrant 4? Now, the fact that cosine is positive means that x is positive, which means we've got to be in quadrant 1 or 4. Oops, it's bigger than I thought. Okay, so that comes from the cosine thing. So the cotangent thing then kicks in. If cotangent is positive, then where are we? Well, cotangent is the reciprocal of tangent. Tangent is positive in the quadrant where we said all, and all students take calculus. Cotangent will be positive when all are positive. This thing is too big. All right, all students take. Take is where tangent is positive. So cotangent is positive in these two spots. So obviously our angle has to live in the one quadrant where both given pieces of information can be true. So this is true in quadrant 1. This is true in quadrant 1. So we must be in quadrant 1. So here's angle theta. Now what that means is y is positive. We'll throw away the negative possibility and we'll say no, it's just positive root 5. So x, y, and r are all positive. We're in quadrant 1, so everybody's positive. So the sine then is going to be root 5 over 3. And the tangent is going to be root 5 over 2. But there, you did it. You found sine, you found tangent. And I'm sure you understand that I'll probably ask you to find cosecant as well. Probably ask you to find cotangent as well. So that by the time you're done, you have everybody. So who am I missing? Sine, cosecant. Oh, cosine itself. Well, cosine's already on the list, so I guess I wouldn't ask. But cosecant would be the reciprocal of sine, so it would be 3 over root 5. Don't leave your answer like that, though. It would be 3 root 5 over normal 5. Cotangent would be the reciprocal of tangent, so it would be 2 root 5 over normal 5. But there you go. You found them all. Let's do more of these because they're very important. Where am I? Here. Alright, I don't know how many of these I gotta do, but let's make room for a bunch of them. Oh, I duplicated it with all the garbage. That was smart. Alright, scroll down. Look, there's a 44. That's even, so I guess I'm not doing it. Here's 45. Let's do this one. So this one mentions find tangent and find secant. Okay, sure. Now the given information is that we know sine, and it's negative. So a big question I got from a lot of people was, if sine is y over r, well, how do I know which one of these values is negative? Because if I have a negative fraction, I don't know if that's negative 2 over positive 5, or if it's positive 2 over negative 5. Either one of those could be negative 2/5, right? Well, alright, this is easily answered. Radii can't be negative, so it ain't this. The 5 has to be positive, which means the y has to be negative. So in our search for x and y and r, we know the radius to be 5, we know the r value to be negative 2. So in our search of what quadrant are we in, a negative y means we're living down here in 3 or 4. Alright, so how do I hammer it down between 3 and 4? Oh, right, there's another piece of info right here where it says cosine is positive. Well, cosine is based on positive x values, so I guess that means we could be in quadrant 1 or 4, and then look at that overlap. It's in quadrant 4. So our angle theta must be an angle that lives down here in quadrant 4, which means our x value should be positive. So we can do the math. We know that x squared plus y squared equals r squared. So x squared plus 4 equals 25. So x equals the square root of 21. And technically it's plus or minus, but we know it's minus because we're supposed to be down here in quadrant. Oh, super psych. Sorry. This is an x coordinate, so it's positive. It's positive because we're to the right. So leave it positive at root 21. Okay, we're done. We now know that tangent is y over x, so it's negative 2 over root 21, which if I rationalize my denominator will be negative 2 root 21 over normal 21. There's your tangent. Secant is reciprocal of cosine, so it's r over x, which is 5 over root 21, which is 5 root 21 over normal 21. Okay, so those are the two they asked for. Again, just make sure that you could find all 6 if you needed to. That's 45. So 47 would be the last one. So we're given cotangent. And it's negative 4/3. And so this might be the trickiest situation because this is x over y. Yeah. So is it a negative 4 over a positive 3? Or is it a positive 4 over a negative 3? Both of these are possible. Negative x's and positive y's, that's happening in quadrant 2. Positive y's but negative x's, that's happening in, oh, I'm saying that backwards. Positive x's, negative y's is down in quadrant 4. So I actually don't really have clarity on which quadrant I'm in at all, but that's fine because we didn't for the other problems either. You need the other rule. So cotangent being negative just meant that we were in quadrant 2 or 4, but then it says cosine is negative, and cosine is x's, so cosine can only be negative over here, and so we've got our overlap now. We know that we live in quadrant 2, and because we're in quadrant 2, our x and y must be a negative x with a positive y. So negative 4 is the x coordinate, yep, and 3 is the y coordinate. And if you guys remember, we talked about Pythagorean triples. 3, 4, 5 is a Pythagorean triple. So you should know instantly that your radius is 5. If you don't, that's fine. But we would do 3 squared to get 9. 4 squared gives 16. That would equal r squared. Remember, it's x squared plus y squared equals r squared. So you can just do that fast. But there's 25. Take the square root. There's your 5. 3, 4, 5 triple. All right, now they want secant. You got it. If you want secant, then you want the reciprocal of cosine, which means you want r over x, which means you want 5 over negative 4. Please don't leave your answers like this. You don't have negative denominators. What you have are fractions that are negative. Pull your negatives out in front, okay? Write it correctly, please. They also want cosecant. Cosecant's reciprocal of sine, so it'll be y over r. I said that backwards, it's r over y. So it's going to be 5 over 3. And that's it, easy peasy. All right, I think that brings us to a close. Yeah, that's just a duplication of the page. We're over an hour now. We're well over an hour. So I was going to end this video and I was going to start again, and we'll do the lesson on unit circle and evaluating trig. So yeah, see you later.